Thank you so much. And thanks for having me. It's great to join you all. Let me share my screen so you can start to see my slides. So unfortunately, I am from the UK, so I have had to do this virtually today, but it is still great to join you all and to be part of All Things Open. I believe there's also an IBM booth, so if you haven't been to the expo floor yet and seen the IBM booths and all my colleagues there, then definitely go and check that out. I also hope you are enjoying my awful photoshopping skills here in trying to make a slide that looks like it's sort of on theme with me as an astronaut. So in this session today, I'm going to be talking about, okay, how do we launch our applications into this really reactive and event-centric world? How do we go about really designing our applications to gracefully deal with these huge quantities of data and reactively respond to events and state changes within our system? Now, I will try and answer questions at the end of this session. If you have any throughout, feel free to stick them in the chat functionality. I've got that open as well, so I will try and monitor that, but I will also look at it at the end of the session. So feel free to put them in throughout the session as you think of them. If I don't get around to answering any questions, my Twitter handle is on this first page, and I believe also on the last one. It's at Grace Jansen 27. Feel free to follow me on there or tweet me, message me, ask me any questions you might have either today or anytime after. So let's get started taking a look at this topic. So first things first, let's get some coffee. It's afternoon time. People are getting sluggish at the conference. It's about 7 p.m. here, so I definitely need a coffee. So let's take a look at a barista example for our sort of systems view of why we need event-driven architecture and where Reactive comes into this. So here we have a barista coffee shop. So this is a demo that you can actually access. It's on GitHub, it's open source, so feel free to go check that out. The link's at the top. It's been created by our cousins over at Red Hat. So in this original version of the application, we have coffee lovers coming in and making coffee orders to a coffee shop via HTTP. They're then passing those coffee orders on to the barista via HTTP. Now, the issue with this is that it's essentially a blocking process. So in this case, as our coffee lovers come in, they're going to have to stand at the till and wait for the barista to take their order in the coffee shop, then to pass it on to the barista making the coffee. They're going to have to wait for that barista to completely fulfill their order, bring the coffee back until they can move on to the next person and they can go and sit down. So not only are you wasting the barista's time because they can only do one coffee at a time, and they're, you've got the waiting time of waiting for the coffee to brew in the machine, and also the coffee lovers are stuck at the till wasting their time, wasting that resource. So instead, what we can do is we can implement event-driven architecture here to help with this. So event-driven architecture, for those of you who've not come across it before, it's a really popular architectural approach, and it's really about enabling events to be placed at the very heart of the system. So when I say event, what I mean is essentially a record of something that's happened. So a change in state that's occurred within a component of your application. Usually these events are immutable and they can't be edited. So when a state changes again, you then just append a new event to the end of your event backbone or your event log. And usually they're ordered in sequence of their creation. So here, for example, we've got a basic architectural diagram of what an EDA approach might look like. EDA stands for event-driven architecture. And essentially what we've got here is we've got microservices. Some of them publish to the event backbone. Some of them might consume events from that backbone, and some might be both. They might consume events, do some kind of processing, and then publish new events to that same backbone as well. So it's really all about having a system of very loosely coupled microservices that exchange information between each other through this production and consumption of events. So it's all about enabling this non-blocking asynchronous behavior. So let's take a look at what happens when we introduce that into our barista example. So you can see here, we've kept the HTTP between the coffee lovers and the coffee shop, but now we've introduced the event-driven backbone or the event-driven architecture into that second stage. So now when our coffee lovers come in and order their coffee, the coffee orders are added to this queue, essentially, this event backlog, and the baristas can dynamically read from this queue as and when they're available. And now our coffee lovers don't have to wait at the till. They can go and sit down and discuss Java, as we all love to do in our free time. And they can just periodically check back on the board to see whether their coffee is done or not. They don't have to get up. They don't have to waste time and resources. The baristas can be more efficient in terms of being able to dynamically get that coffee order on the go. And essentially, we're creating a much more asynchronous system here. And you can enable that behavior using various different tools. One of the most popular open source tools available for event-driven architecture is Apache Kafka. So many of you might have heard of this before. If you haven't, it's an open source distributed streaming platform. So it is a way of creating that event log, that event backbone, and enabling the asynchronous communication right at the very heart of your system. Its data is immutable, and so it has this stream history. So essentially, events just get appended every time a new state occurs, and it means that you can read back throughout that stream history to see which states have changed and when. It also enables high availability of your data and your events, and scalable consumption as well. So some of you might be asking, okay, so now that I've introduced Kafka into my application or introduced event-driven architecture, does this now mean my coffee shop is non-blocking and highly responsive? This essentially translates as, okay, is my microservice system non-blocking and highly responsive? And often people jump to the conclusion of, well, yeah, I'm using Kafka, it's great. Unfortunately, that's not the whole story. Kafka is a fantastic tool to start with, but it isn't good enough to just have a good tool. You need to use it in the right way, but you also have to think about your entire application as a whole. You have to think about the various layers and levels and whether you've introduced this asynchronous and non-blocking behavior into every interaction within your application. So this is where things like reactive systems can come in handy and can really enable you to introduce that asynchronous behavior at every level of your application, not just that data level where Kafka tends to sit. So reactive systems, what are they? Well, generally they're based on the Reactive Manifesto, which is essentially 4 key characteristics or behaviors that were essentially brainstormed to say, okay, what do we really need if we're going to make a really responsive application? So in 2013, this manifesto was made and these core behaviors were established. So the underlying behavior is this message-driven asynchronous communication really at the heart of a system. And it's the behavior that enables the other characteristics within reactive applications. Now, interestingly, in the original manifesto, this was actually event-driven, but they switched in 2014 when they introduced Reactive Manifesto 2.0 to message-driven. And if you want to find out why they made that switch, you can read, there's an entire article online that you can check out that explains that move. But is there a difference and does it really matter? So I've detailed out a definition for each. So for messages, I've described it as an item of data sent to a specific location. So it's really about that specificity and who that message is being sent to. And then I've defined events as a signal emitted by a component upon reaching a given state. So that's more about a broadcast rather than a direct specific message. But actually, interestingly, you can have a system where you have a message that can contain an encoded event in its payload. So you can kind of have this weird mesh of both as well. But actually, when it comes to utilizing tools like Apache Kafka, it really doesn't matter which type you use, because Apache Kafka doesn't specify whether it's messages or events that you're utilizing. Instead, it just refers to them as records. So it says about, if you use Apache Kafka, you can publish and subscribe to streams of records. You can also store records and process streams of records. So actually, Apache Kafka can be used for both message-driven and event-driven architecture. And that means that it makes a fantastic base for that underlying key reactive characteristic. So just using Apache Kafka can give us at least one sort of behavior of reactive systems. But as I said, there's 3 other behaviors, and they are quite important to add on top of this underlying asynchronicity. Let's take a look at why we need those other behaviors. So going back to our barista example, here we just have 3 coffee lovers. But there aren't 3 coffee lovers in the world. There are loads of coffee lovers. So what happens at rush hour when everyone wants their coffee? Now, we get this influx of coffee lovers coming in and placing orders. And although we've introduced this asynchronicity in terms of being able to add them to our event backbone so our coffee lovers can go and sit down, we still have a point of contention in our system. We only have one barista making all of these coffees. And so they're going to be a blocker on how efficiently and how fast we can get those coffee orders out. So this becomes a potential point of contention, stress on our system, and a potential bottleneck as well. And even potentially at some point, a potential failure point, because what if that barista service goes down, for example, or becomes stuck in a process? So actually what we need to introduce here is this characteristic of elasticity. Now notice it's not just about scalability, but elasticity, and that's a deliberate choice in words. That's because in the Reactive Manifesto, it's not just about scaling up, it's also about being able to elastically scale down as well, depending on your fluctuating load. So as your load increases, being able to dynamically assign resource to be able to efficiently and gracefully deal with that load, but also when that load decreases, being cost effective in being able to scale down those resources as well. So if we were to introduce that behavior into our application, we'd see something more like this. So we might be able to scale up the number of barista services. So now we've got 4 baristas making all those coffees. So now we can gracefully handle that increase in load and be able to basically provide a much more responsive and reactive application to our end users, in this case, those coffee lovers. Let's take a look at another example of why we need some of the other characteristics of the Reactive Manifesto. So in this example, I've added in an additional component into our barista service. And in this case, I've added in a coffee serving table. Now, in this example, the coffee serving table is where the barista has to place the coffees before they can then be told that they're ready for the customers to collect. This is sort of representative of, say, a downstream microservice that might be doing some additional processing, or perhaps a third-party service, or even, for example, a database. It can be anything where you need to sort of pass on those records or messages to an additional component within your application. So what happens when that additional component, in this case, the coffee serving table, gets full? So in this case, no one's collecting their coffees. They're being a bit lazy, being a bit slow. So it's built up on the coffee table. So now the barista is juggling coffee because they can't put it down on the table. So now the barista's stuck because they can't make any more coffee because they're juggling and holding them all. The coffee table isn't doing anything. It's not getting rid of the coffees. So again, we've got a point of contention here, a potential point of failure and unresponsiveness within our application. This is representative of, say, that downstream component maybe being unresponsive, going down for a particular reason, or not being able to access it at all. So what do we do in this situation? Well, we need to build in resiliency into our application, building in resilient behaviors. So in the face of failure, we can gracefully deal with that rather than collapsing and failing and having an unresponsive application. So in the case of our barista example, we could perhaps add in fallback behavior. So it might say, okay, when that barista becomes full because the coffee table's gone down, let's instantiate a new version of the coffee table and add more baristas, for example, to get through that backlog. So adding in resilient behaviors can help us to gracefully deal with failures and enable our applications to remain responsive to our end users. And that's the last characteristic, responsiveness. You can see how these underlying characteristics can lead to creating an application that's really responsive to events and state changes within our application and provide that really reactive user experience to our end users. So by enabling these behaviors within our application, we can enable our applications to be really reactive and responsive, have that asynchronicity and that non-blocking nature. And actually, Kafka does do this to a certain extent. Kafka does enable some of these characteristics by itself. Like we saw before, it does enable that asynchronicity that we need at the very base of it, at the core of our system, as we show here in the Reactive Manifesto. Kafka also has some built-in elasticity. So for example, it's able to scale up the number of brokers it has, the number of partitions. There is some scalability within Kafka as well. There's some resiliency as well. So in Kafka, you usually have your records, for example, being stored on partitions, and those partitions are spread across different brokers. Normally you'll have a leader broker and then at least 2, if not more, follower brokers. And your application connects into the leader broker and then your records are duplicated across the partitions on the other various brokers. Now, by having replication throughout those brokers, it means if one broker were to go down, you still have replications of those records, and so you haven't lost that history at all. As well as that, with the leader-follower type of model that they're using, if the leader were to go down, which is how your application connects into Kafka, it doesn't matter too much because Kafka has an inbuilt leader election policy. So what it means is that if that leader were to go down, Kafka automatically assigns one of the followers to become the new leader. So your application doesn't lose connection to Kafka and you can continue on as normal. And when the broker comes back up again, then you can assign it to be a follower. So all of these behaviors do enable the reactive characteristics at some level. But as I said, it's not just about the data layer. You have to think about how the individual microservices or components within your application communicate to each other and how your system as a whole has enabled those asynchronous and non-blocking behaviors and characteristics. So to enable that throughout your application, you can utilize reactive frameworks and toolkits in addition to utilizing Kafka. So using them in conjunction with one another. We're going to take a look at a couple within this session, but they aren't limited to just these. So this isn't a complete list. So the two we're going to take a look at are MicroProfile Reactive Messaging and Vert.x Kafka Client. Now, as I said, this isn't a full list. There are others available. So for example, if you're using an Akka-based system, you might be interested in the Alpaca Kafka connector. If you're already using Spring, for example, you might be interested in Spring Webflux or Project Reactor. But in this session, we're just going to take a look at MicroProfile and Vert.x. These are two open source projects that you can utilize to connect your applications with Kafka and enable those reactive behaviors throughout your application. So the first one I mentioned there is Eclipse MicroProfile. And as the name suggests, this is an Eclipse project. So it is completely open source, and it really is a community-driven specification. And it's designed to enable enterprise Java applications to be successfully developed for the cloud as microservices. It's developed by a wide range of individuals, organizations, and vendors, including companies like IBM and Red Hat, for example. So there's a huge variety of people who are contributing to this from all over the globe, meaning that this project has a huge amount of innovation and has evolved really successfully over time. So what do you get with MicroProfile? So you get various different APIs and components that can really help you to develop an effective cloud native application. And they work really well with Java EE, for example, or Jakarta EE. So as standard, you get this standard stack at the bottom here. And this comes as standard with the MicroProfile 4.0 stack. 4.0 is the latest major release of MicroProfile, but I believe there's 4.1 already out, and I think 4.2 is planned. So as well as this standard stack, which includes some Jakarta EE specifications and APIs, Jakarta EE is another enterprise Java open source specification to enable those sort of microservice-based APIs that you might need. But on top of that, it also introduces additional APIs like health check, for example, and metrics, which are really useful when you're using distributed systems like the cloud. It enables things like external configuration, authentication through JWT, open tracing, fault tolerance, etc. So lots of really useful APIs there. Now, as well as the standard stack, we also have the standalone projects that the MicroProfile community contributes to. Now, they aren't yet part of that standard stack, but it's hoped that one day they will become integrated and part of the standard. So these individual projects are being developed by the same community, but they're just sort of on their own at the moment. The one we're interested in is Reactive Messaging 2.0. Now, that is essentially, it utilizes annotations to be able to introduce those reactive behaviors and characteristics throughout your application, the communication you use between microservices and also from microservices to external components as well, like external messaging brokers like Kafka. Reactive messaging, the API makes use of and interoperates with two other specifications. One is another MicroProfile standalone project, which is the MicroProfile Reactive Streams Operators. This is a MicroProfile specification which builds on top of the Reactive Stream specification, which is outside of the MicroProfile community. It provides a basic set of operators to link different reactive components together and to perform processing on the data which passes between them. Now, the reactive stream specification, which is outside of MicroProfile, but still used by the components within it, is really, again, another community-driven specification to enable asynchronous data stream processing with back pressure, which is really important in reactive applications. If you've not come across back pressure before, it's a process in which a downstream component can provide feedback to an upstream component. So if that component's becoming overloaded or stressed, or is stuck in a process, for example, it can feed that back upstream to slow the rate at which requests are coming to it, for example. So it's really useful in ensuring that we don't have contention points or bottlenecks within our system. So you can utilize reactive messaging through the annotations that I mentioned. So in MicroProfile reactive messaging, an application's beans methods are annotated with either @incoming or @outgoing annotations. As the name suggests, they are either @incoming is when you're subscribing to a particular channel of some kind. So you're subscribing to messages or records or events, and outgoing is when you're publishing them. These annotated methods are then connected together via something called channels. These channels are essentially just opaque strings, so you can name them what you want. You can see in the diagram below, for example, we've connected method A with method B through the channel of order. You can see it's connected there through the @outgoing and @incoming annotations there. There are two types of channels, either internal or external. Internal is when you're connecting two components or microservices within your application together for communication, like we're doing at the bottom here. That's just called a channel. If, however, you're connecting to an external component, like an external messaging broker, like Kafka, for example, we call that an external channel, and it's called a connector. Now, because MicroProfile is a specification, you'll need an implementation to be able to actually use it. So we have implementations within OpenLiberty, for example, which is our open source runtime for Java, and that has its own connectors. So depending on the implementation you choose will depend on what connectors are available to you and what types of third-party messaging brokers you can connect to. So if we get time at the end, I'll run through a MicroProfile lab that utilizes the Liberty Kafka connector, because I'm connecting in an OpenLiberty application with Kafka, as the name suggests. The other framework I wanted to introduce you to is Eclipse Vert.x. Now, unlike the previous example with MicroProfile, which is specifically for Java, enterprise Java applications, this is a polyglot toolkit. So instead, it can, as well as being used for Java, it can also be used for things like JavaScript, Groovy, Scala, Kotlin, and other languages. It's based on something called the reactor pattern. So this is essentially, basically puts event-driven architecture really at the heart of this pattern. So it uses a single threaded event loop, which blocks on resource emitting events and then dispatches them to corresponding handlers and callbacks. So it receives messages or requests and connections coming from multiple concurrent clients and processes these posts sequentially using these event handlers. So it really is sort of event driven at the heart, and it's single threaded, which can be really useful if you have, say, threading headaches when it comes to your application. It runs on the JVM, and it's non-blocking and event driven, like I mentioned. So actually it was Vert.x that we used for one of our first demo applications of this. It was essentially a colleague of mine came together, and she was creating a demo application for Kafka just to check that her Kafka was working. And I suggested, okay, why don't you try turning that into a reactive application and see what benefits you get from it? So we took her basic non-reactive demo application, it was based on Java, and we've converted that using Vert.x into a reactive application. So the architecture of it looks a little bit like this. This is all open source, including the fancy UI. So if you want to go and check it out, the GitHub link is on these slides. So essentially what we created was a Vert.x application that produces events to Kafka and then kind of weirdly consumes its own events. Now, that's not necessarily what you'd want to do in production, because Kafka doesn't really play much of a role there. You're probably going to be consuming someone else's events or some other topic's events. But in this case, it's just to check that our Kafka is working. So it is just trying to make it as simple as possible. And then we've connected in a UI via a WebSocket to our application to be able to start producing, stop consuming, stop consuming, and enter a custom payload for our events. So as I mentioned, it's all on GitHub. So if you do want to check it out, head to that link there and you can see it for yourself. Now, taking a look at this application in action. So as I mentioned, we created this UI to be able to enable us to check that our Kafka is working by enabling us to basically tell our system to either start producing, start consuming, stop producing, and stop consuming, and enter those custom payloads. Now, the issue with the starting and stopping meant that we had quite a few headaches when it came to thread handling within our application. However, actually, we massively benefited by using Vert.x in this case from that. So let's take a look at the benefits of what happened when we switched to utilizing Vert.x under the covers. So in our original application, we were having to use a for loop inside a while loop to be able to access the records and basically consume them from our Kafka broker. So it was essentially like the following flow. So we had to poll for records, and then the poll function returned a batch of records, and then we had to iterate through each record within that batch, and for each record, send that record along the WebSocket to the front end to be able to display it, like we saw on the right-hand side there when we started consuming. Then, after we completely iterated through all of the records in the batch, we could return to step 1 and start polling for records again. But what this process meant is that whilst we were processing the current batch of records, no new records could be fetched from Kafka. So that meant that we had sort of this blocking process, and it wasn't particularly asynchronous. Instead, when we were able to introduce Kafka, we were able to introduce far more asynchronicity into our process and actually simplify our application logic. So this time we could essentially, we were using a handler function that was going to be called every time a new record arrived. Again, allowing much more asynchronicity and to be much more aligned with the reactive paradigm. So this made our flow a lot simpler. Vert.x was now what was handling the step of polling for new records. So that wasn't in our own application logic. So now we were able to receive a new record and then immediately send that record along the WebSocket to the front end. So not only did it allow the application to process on a per record basis, but it also left us free as developers to focus on just the processing of the records rather than focusing on polling and consuming them from Kafka. So that really freed us up, as well as enabling us to be more asynchronous. As well as that, as I mentioned before, we wanted the ability to be able to pause and resume both the producing and the consuming records from the front end. In the original application, where the default Java Kafka client was used, the while loop that you saw earlier that calls the poll for the consumer needed to be exited and then resumed based on the commands from the front ends. And because the client is single threaded, the loop had to be executed in a separate thread to the main flow of the application. Because we wanted to produce records on a timer, a similar while loop in a separate thread was required for the producer. So we had to deal with this headache of writing logic to control this thread lifecycle and essentially synchronize data across the threads just to get control over this flow of records. So when we introduced Vert.x, we were actually able to use a combination of Vert.x features as well as the Vert.x Kafka client features to make this flow control much, much easier. So for the producer, for example, we used a feature in Vert.x that allows a handler to be called on a timer basis. So now we've got the handler, it could be called once or multiple times. It was much easier for us to be able to pause and resume the timer when start and stop requests arrived from the WebSocket. For the consumer, for example, we used a built-in back pressure support, like I mentioned that back pressure earlier, and that allowed the consumers to be paused and resumed. So when a stop command comes from the WebSocket, the consumers paused and the Vert.x clients will stop polling for new records from Kafka. And then at a later time, when you want to resume it, the Vert.x client will then resume polling and the existing handler will start receiving new records. So you can see there we were able to introduce again, much simpler logic flow within our application and asynchronicity. If you want to find out more about, or more in depth, about the various advantages we gained from switching from a non-reactive to reactive, utilizing the Vert.x framework, then check out our article here where we go into it in a lot more detail. Now, as I mentioned, I also have a MicroProfile interactive demo. Now, this is focusing on the MicroProfile reactive messaging API that I mentioned earlier. So in this, you can utilize our online environment, which is, we've named it Skills Network Lab. So it means that if you want to do this in your own time, you can too. So as an example, we've got lots of different labs. This is just one of them. And we run it all within a browser. So you don't have to have any prerequisites installed in a local machine. On the left-hand side, you have instructions. And on the right-hand side, you have your IDE and your terminal. Now, if you want to access that, the link is here. And I'll share my slides afterwards as well if you want to access it in your own time. There are also lots of other labs that you can do within this as well. So if I switch now to, I'm going to end my slideshow to be able to switch to that demo. So as I said, I've skipped a few steps just to make this a bit quicker. And what I've done is I've just already git cloned the repo and I've gone into the correct directory. So in all of these, you'll find that we have a finish and a start directory. The finish directory is what you should achieve at the end of the lab. So if you want to check your work at any point, feel free to access that. But we're going to go straight into the start directory, which is the unfinished application that needs the steps within this lab to complete it. So in this application, in fact, I'll go back just so you can see what the application is like. So we've tried to use a very similar application for all of these labs to make it easy for you to focus on the technology rather than trying to worry about what the application's doing. So we've got two microservices within this application, a system microservice and an inventory microservice. The system microservice just gets your average system load and produces that as an event, in this case to Kafka. And then your inventory microservice consumes those events from Kafka and essentially stores the latest version of your system load data. We can then access that through a RESTful endpoint. So what we're going to be doing in this is introducing this reactive MicroProfile reactive messaging behavior in the communication between those two microservices and our external messaging broker, Apache Kafka. So because we're using an external messaging broker, we're going to be utilizing the external channels called connectors within this demo today. So I'm going to skip straight ahead to number 4, which is where I was. So the first microservice we're going to edit is the system microservice. So the first thing we need to do is create the system service class. Now we've tried to make this as easy as possible for you. I'm just going to make this slightly smaller so I can see the edge of my screen. Otherwise, I'm going to lose those commands at the end. I've not copied the whole thing. There's a copy button here, which helps. So you don't have to highlight the whole thing. You can just use this copy button on the left-hand side and just paste that in to your terminal on the right. So you should see that actually when I create that, a U will appear for any new files. So you can easily find them within our directory levels here. Otherwise, there is sort of a laid out directory path that you can follow if you want to do it that way. So now I can open up this new file. I should see it's empty because I've just made it. I haven't put anything in it yet. And we provided all the text, all the code that you need to insert into this file. You can just exclude that globally. So because this is the system microservice and we're the ones that are producing events to Kafka, we're utilizing that outgoing annotation from MicroProfile reactive messaging within this class file. And you can see we've got the import up here for that as well. We're also making use of something called reactive streams, which was that specification that I mentioned earlier. And we're also making use of RxJava, which is a reactive programming library. So that enables those reactive characteristics and behaviors at the very sort of bottom layer, that programming level within your programming logic. So in this case, we're utilizing a method called flowable, which essentially allows us to add back pressure in to our application. So where we've got it down here, you can see there, we're able to essentially fetch that system load data on a timer basis. So every 15 seconds in this case, we've been able to introduce back pressure because of the method that we're using, flowable. So now we've got something like this where we've created a system service class within our system microservice, and we're able to utilize that outgoing annotation to connect in to our system load topic within Kafka. So let's create a similar thing for the inventory microservice, but this time we're going to be consuming instead of producing records to Kafka. So now that I've created that file, I can go back to my Explorer, close up system, and I'm heading into inventory this time. So again, just open it up where it says U. It's quite easy to follow, and then you'll find the new file here. You can make this bigger if you want to see the whole names. I'm just keeping it small for just now, just to save space so you can see the code more easily. So copy and paste in what we've given you here. And this time round, what you'll notice is that we've actually utilized the @incoming annotation. I'll make this smaller so you can see it. So we've utilized the @incoming annotation because we're consuming events from Kafka, but we're still consuming from the same Kafka topic because, as I mentioned, we're just producing and consuming our own events here. Now, again, you can see at the very top that we're utilizing, we've imported that MicroProfile incoming annotation. And you can read more about the various different sort of methods that we've included within this class file if you'd like to. We put more detail on the left-hand side here, and you can read that in more detail in your own time. So now that we've created that, what we've done is we've now got a connection from Kafka to our inventory microservice via that incoming annotation. So the next thing we need to do is add some configuration. So in order for them to exchange messages with the external messaging system, we need to create MicroProfile Reactive Messaging Connector API to be able to connect those together. So we need to add some configuration keys to a properties file for each of these services for them to be able to do that connection. So we're going to be utilizing MicroProfile configuration, which is another MicroProfile API. We have a whole guide on that if you'd like to go into that in more detail. So first things first, we need to create an external configuration file, and that's within the system microservice. That's the one we're doing first. So go back to system, and then go down to close up Java and go into resources this time around. And you'll see it appear here. Should be empty. That's the sign that is the file you've just created. And then copy in the config values we provided for you. Remember to save all of these. Our IDE doesn't save automatically, so make sure you're saving as you go along if you're going to do this in your own time. You can notice that we're utilizing the outgoing annotation. So that's why we've got outgoing within our config here, because this is for the system microservice that's producing events. We're utilizing a connector because we're connecting into an external messaging broker. So you can see we've got Liberty Kafka because we're connecting an Open Liberty application with Kafka. And you can see we've also specified the topic that we're producing to within Kafka here as well. Now we've also got these two values, which are serializers, and that's because it explains it here. Essentially what it does is it implements logic for turning an object into JSON, which is what's needed essentially for Kafka. So we need to do the same thing for the inventory microservice next. So we can go ahead and create a very similar file, but this time within inventory. So head into the inventory directory. And again, don't go into Java, go into resources, and then you'll see MicroProfile config properties file appear there. It's a very similar configuration file, but this time around we're using the incoming annotation, hence incoming in this config file. We're still using the same connector because we're still connecting a Liberty application with Kafka, and we're still using the same topic in Kafka because we're still consuming our own events. So we still want to read from the same topic. We've got a deserializer this time because we're going the opposite way from JSON into a Java object. And we've also got an additional configuration value here because it's a consumer. Now in Kafka, Kafka has this topic, concept of consumer groups, which allows your consumers to be grouped together if they are reading from the same topic. And what that allows is it allows you to have ordering guarantees. So it makes sure that your events or messages or records are read in order. And it means you can guarantee that you won't have duplication of processing of a particular record or event. So if we were to have multiple inventory microservices, they could join the same group, consumer group, by using the same group ID in this configuration. So the next thing we need to do is configure our server. So to do this, we need to create a server.xml file. Now we're only doing this for the server microservice, because the system microservice, sorry, because it is exactly the same for the inventory microservice. So we've already done it for you. So let's take a look at this. Instead, you want to head into not resources, but Liberty this time, head into the server.xml and copy that over. So here you can see that we're utilizing features like the reactive messaging one, but we're also making use of quite a few other Jakarta EE and MicroProfile features within this as well. I already mentioned configuration as one example. So as I mentioned, the inventory microservice already has the same file set up for you. The next thing to do is to get it ready to be able to build your application. So we need to create a pom.xml file where we can put all of our dependencies. So I'm creating this for system. So you need to head into system, and then you can see the pom.xml file just within that directory directly. So open that up. Don't open the one below it. Make sure you're opening the correct pom.xml. It should be empty, and that should be a sign that it's the correct one. And then copy in all the dependencies we need. So if I copy and paste that over, so you can see here that we're utilizing dependencies like, for example, there's that Rx Java, which was that reactive programming library that we were using for flowable and back pressure. We're also making use of the reactive messaging dependency, which is separate from the Eclipse MicroProfile dependency because it's not yet part of that standard stack. It's a standalone project. So make sure you've got those two dependencies if you want to use both. And that's how simple it is. After that, we can do things like we can build our application and test it out. But hopefully what that's shown you, just given the time restraints we have within this session, is that it's fairly easy to go ahead and create a reactive application by using these open source frameworks in addition to Kafka as well. So in summary, hopefully what I've shown you is that non-reactive applications, when you just shove in Kafka, it doesn't necessarily make an entirely reactive application. The reactive characteristics and Kafka do go hand in hand, but it can be really useful to utilize things like those reactive frameworks and toolkits that I showed on top of Kafka to really enable that asynchronicity, non-blocking reactive behavior end-to-end throughout your application. But you're not alone. The open source reactive community is on hand to help, and there are various different frameworks and toolkits you can utilize. If you want to take a look at some of our other reactive labs, so the lab I showed you today and all of our other sort of labs hosted in that environment are based on the Open Liberty guides. So you can head on over to the Open Liberty website and search in the search box for reactive, and it will show you all the reactive guides if you're interested. If you want a summary of everything I've gone through today, I've authored a really short ebook that basically covers what reactive systems are. And so it's a good recap, when you might want to use them and how to go about using them. And you can access that through the link here. And I believe they might also be giving them out on the IBM stand as well. So feel free to head over there and ask about that. And as if I haven't given you enough links within this presentation, if you are really keen and want to learn more about anything I've mentioned within this session, I've got some useful links here for you. So with that, thank you very much. Hopefully you found the session interesting. And if anyone has any questions, I'd be happy to take them now. I haven't seen any in the chat yet, so. Anyone got any questions? Oh, thank you so much, Chris. Thank you for the feedback. Yeah, if anyone has any feedback at all, feel free to stick that in the chat as well. And if anyone thinks of questions later, maybe you don't want to ask in a public forum, or maybe you just think of them in another time, my Twitter handle is there. Feel free to reach out to me on Twitter and I will get back to you. Cool. Well, if nobody has any other questions, thanks for joining me, guys.